All right, guys, I am back with another example. We're going to do our acetate polyatomic ion. That's one we learned a long time ago in nomenclature. So it's our C2H3O2 minus. Sometimes you might see it written this way, so it helps you figure out what's bonded to what. So CH3, COO minus, okay? So first things first, we need to total up our valence electrons. So looking at your periodic table, okay, we've got 4 valence electrons here. Hydrogen has 1, but there's 3 hydrogens. Here's another carbon with 4. And then oxygen has 6. This oxygen has another 6, and then this is a negative charge. It's not a neutral molecule, so we need to add 1. So we need to add up all of these things together. So we've got 4 and 3 is 7, and another 4 is 11, and then I'm going to add that 1 over there. That's 12, plus another 12. So we've got a total of 24 valence electrons to use in our picture. Can't use more than 24, can't use less than 24. Now, in terms of our central atoms, carbon is always central, no matter the reason. Okay, so in the previous example, we said, okay, the central atom is usually the least abundant. Okay, now here you've got 2 carbons and 2 oxygens. So carbon is the backbone of life. So carbon's always central, and we have 2 carbons. So I'm going to bond them together. Now here it's saying this carbon has 3 hydrogens attached to it. So I'm gonna write 3 hydrogens right here. And then this carbon has 2 oxygens attached to it. Okay. Now, again, always attach everything first with single bonds. We can always go back and fix our picture if we need to. So we did single bonds. Now we need to satisfy the octet rule for everybody except for hydrogen. Hydrogen follows the duet rule, can only have a single bond attached to it. This carbon has 2, 4, 6, 8. That's good. What about this carbon? 2, 4, 6. Let's add another 2 for 8. Okay. And then we need to put 3 more pairs around our oxygens. So oxygen has 2, 4, 6, 8, and this oxygen right here as well. Now, if I go back and check, okay, and then of course some people are going, oh, you forgot the brackets with your charge. There it is. Now, if we recount how many we used, let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. This is 26 electrons. We can't have that. Okay, so if you use too many, that means there is multiple bonding. So we add 1 double bond at a time, fix our octets, and then see if we need to add another one or maybe a triple, so on and so forth. Okay. Now, some people go, well, what about a double bond there? Can't do that because carbon cannot violate the octet rule. It's in period 2. So that leaves us 2 options. Put a double bond here or put a double bond there. And both of those would be correct. Okay, so let's draw that out. Okay, now instead of that lone pair there, I'm going to put a double bond to this oxygen right there, and I need to fix my octet. So I would just have 2 lone pairs now on oxygen. And then this second oxygen here still has its 3 pairs right there. So we got rid of this lone pair on carbon here, and we got rid of a lone pair there on oxygen. So everybody has their octet. Okay, and now this is 24 electrons. So this is 24 total electrons. And now we're going to answer some questions about this. So first things first is I want to know who has this negative formal charge. Okay, and this is not a neutral molecule. Okay, so let's check our formal charges. So let's check our carbons. Okay, the valence number of carbon is 4. Okay, and counting once for each bond, because remember these are 2 electrons that are shared. 1 belongs to carbon, 1 belongs to hydrogen. So we have 1, 2, 3, 4. 4 minus 4 is 0. That carbon is neutral. What about this carbon? Valence number of 4 minus half of each bond. So 1, 2, 3, 4. 4 minus 4 is 0. Okay. Now if you put your double bond here, okay, let's count the formal charge of this oxygen. Oxygen has a valence number of 6 minus, again, half of each bond. So 1, 2, 3, 4, 5, 6. That one's also 0 as well. Okay. Now, some of you might have put your double bond here, and so these would be flip-flop. That's called resonance, the movement of lone pair and pi bonds. So this double bond could flip-flop there. We can draw that resonance structure in just a little bit. But let's look at our formal charge of this oxygen. 6 minus, again, once for that single bond. 1, 2, 3, 4, 5, 6, 7. So it's this oxygen right here that is carrying that negative formal charge. Okay. Now let's draw out a resonance structure so you can see how that double bond can resonate. So what I'm going to do in this next little picture here is just quickly redraw this. I'm just going to leave off the brackets for now. I'm going to put my formal charge on that oxygen though. Okay, so I get in the habit of recognizing who's carrying charge. And then I'm going to see, how does that double bond move? Well, what happens is a lone pair here can shift in to make a double bond there. And then this pi bond here can move up there. So that's called resonance. And we're actually showing that in arrows, which we do in organic chemistry. Okay. So some of you may have initially put your double bond right here and then had your single bond right here, and this oxygen right there has got the negative formal charge. So both of these are resonance forms of that acetate ion. Okay, and they're both correct. Okay, we haven't violated any rules. Everybody has their octet. We are good to go. So let's answer some questions about this molecule, okay? So I want to know how many groups are attached to this carbon. So again, a group is an atom or a lone pair. So we have 1, 2, 3, 4 atoms attached to that carbon. So that's 4 groups. Okay? So if we look at our shape sheet, I'm just going to write EG for electronic geometry. 4 groups is associated with the tetrahedral shape. Okay, and what about its molecular geometry? Well, the molecular geometry is also going to be the same thing because there are no lone pairs on that carbon. So I'm going to write the same. Okay. Now, what hybridization is associated with 4 groups? So let's count what carbon would mix of its atomic orbitals. Okay. Because again, orbitals are where those valence electrons are. How many atomic orbitals would it mix to give 4 groups? So S, P, P, P. So that is 4 fingers for 4 groups. So I said SPPP, that would be SP3 hybridized. Now, let's look at how this carbon right here is different. This carbon has a carbon attached, an oxygen attached, and another oxygen. That's 3 groups. Some people go, hey, it's got 4 because they're going 1, 2, 3, 4, and that is incorrect. A group is an atom or a lone pair. It's not these lines that us human beings draw on a piece of paper, right? There's not really lines between atoms, okay? There's just regions of electron density that are overlapping to interact. So 3 groups. What electronic geometry is associated with 3 groups? That would be our flat triangle called trigonal planar if you're looking at your shape sheet. And since carbon has no lone pairs on it, it's the exact same thing. So it kind of has, if we were to redraw this, that 120-degree bond angle between things. It's like a flat triangle, and this is our tetrahedral shape there. Now, what about its hybridization? Well, let's count what we would mix on 3 fingers. So S, P, P. So I only said 2 P's, so that would be SP2. Okay? So some people go, well, what happens to that 3rd P? What's the 3rd P in the molecule doing? Well, that's actually making this second connection here called a pi bond. Okay? So if I want to label my sigma and pi bonds, let's do that. Sigma, 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 sigma. That's the first connection between any 2 atoms. This is sigma. We also have a sigma here because first that carbon had to meet that oxygen. Then they really liked each other, so they interacted their 3rd p orbitals to give this pi bond right there. So we've got a total of 1, 2, 3, 4, 5, 6. We have 6 sigma bonds and 1 pi bond in that acetate ion right there. All right, guys, so you seem to be doing a really good job. So keep sending me those questions if you have any, and I will be talking to you soon. Bye.